Bonjour, welcome back to QX01, Introduction to Quantum Information and its Associated Technologies. So let's have a look at the planning. So far we've covered six lectures, and then we had 2 weeks break. And then we start again. So there's a little bit of a change. We were supposed to have something on quantum cryptography, and hopefully it will be next week. It might not be next week, might be another week, but we'll see. So far, so good. If not, in any case, so today I'm going to carry on what I started on quantum gates. So I will finish that today, and I will most likely start to talk about quantum algorithm and carry on. So the lectures that will be given by colleagues. So one of them should be on quantum cryptography by the company KETS, as I said, and then there will be that is for sure. There will be something on quantum sensors by Thales. This one is also an introduction to the Atos quantum learning machine is confirmed, as well as this one on quantum technologies. And there will be one on quantum algorithm part 2 that I will not do, and that will be done by some colleagues to be determined yet. And the date is also to be determined, but so we'll see. Keep in tune for now. Right, so let's have a look at what we said last time on quantum gates, and I will review briefly what we covered. So we started with the 1 qubit gates that can be done on single qubits. Then we talked about 2 qubit gates, and in particular the C0 gate. Then we also said that there can be more than 2 qubit gates, in particular 3, and the Toffoli and the Friedkin gate. And then we started to go into how we can draw and put together gates into quantum circuits. We already have seen some examples before. And then we started some practical cases. So we saw the first one, which is how we make a Bell state into a quantum circuit, and we just started the one on quantum teleportation that I'm going to do today. And then finally, so in both of these cases, we need the notion of entanglement that we've seen before. And as a side note, I will tell you to finish that lecture on quantum gates, how we can create entanglement in practice with photons. And then I'll move on to quantum algorithm, depending on the time that we have for today. Right, so quickly, 1 qubit gate. So we said these Pauli matrices that we talked about, so the X, Y, and Z gates, together with the identity gate, which is the do-nothing, basically represents a set of 1 qubit gates. And particularly the X Pauli gate can be seen as the NOT gate. And each of them can be seen as a rotation along the X, Y, and Z axis if we go back to the block sphere representation of a qubit. Okay? And basically what we said is that any permutation of these Pauli matrices represent a specific group that we call the Clifford group, which is therefore important in quantum information, and in particular because, as we said, the Pauli matrices X, Y, and Z can generate any 2D dimension Hermitian matrix that can be generated. There's another very important gate, which is the Hadamard gate. So you can see this. So this is a presentation of the Hadamard gate. And we've seen an example what it does to a qubit Q0 with an input 0 or an input 1. What it does basically is it put a given qubit state into a superposition state of 0 and 1, or 0 minus 1, depending on which state you start from. So we can call it, sometimes the Hadamard gate is called the superpositioning gate. As we will see, this gate is very important in order to sort of initialize to go from a classical bit 0 to a quantum bit of 0 plus 1. There are other gates that can be done, like the square root of x or the square root of naught, which looks like this. So the reason is square root is because basically it means that if we take this matrix and we square it, I believe we did that, then you end up with the naught gate. So that's why we call it the square root naught gate. So when we apply it twice, we get the x gate. We have also a more general gate that is than the Pauli matrix gate, which is the phase shift gate, most usually written R phi, which is something like this, where we can change phi depending on the system that we have. So in particular, when phi is pi, then we obtain the z gate. When phi is pi over 2, then we obtain the square root of z, which we call the s gate. And when phi is pi over 4, then we have the t gate, which is the fourth root of z. And the reason why we have these different gates is because, as I said, and we will see that much later on, is because it depends on the physical systems that we implement. For some of them, it might be difficult to do some gates and easier to do others, hence the reason why there are different gates that can be used depending on the different physical systems. Same thing for 2-qubit gates, and in particular the very important one, so-called the control NOT gate or the C0 gate, sometimes also called CX, because we see the X matrix here. So this is a 2-qubit gate, so Q0, Q1, and what you do is you basically, depending on the input of the Q0 qubit, so you have a control bit and a signal qubit, then you change the other qubit depending on, so it's a conditional 2-qubit gate depending on the state of the first one. Okay, and so it's, as a 2-qubit gate, it's a 4x4 matrix, and the representation is given like so. We can have a more generalized C0 gate. It's called the control U gate, which is something like this. It's also a 4x4 matrix, but what you do is you basically have here a U Hermitian matrix with 4 coefficients that can be anything as long as this 2x2 submatrix is Hermitian. And so that means that the C0 gate is basically a particular case of the control U gate. Once again, depends on the systems. For some systems, it's in fact easier to do different gates than the C0 gate that can be seen as a specific U gate. U standing for unitary matrix. And basically, as we will see later on, so today one thing we will see is the so-called De Vincenzo criteria to build a quantum computer. And one of the criteria is that you need a universal set of gates, of single gates and 2-qubit gates. And basically, in order to do so, when you have the Clifford group, so the XYZ and the C0 gate, as well as the Hadamard gate, but basically with those gates, you have a universal set of gates that can provide you with a universal quantum computer, which is ideally what one would like. We have other gates like the swap gate between 2 qubits and the square root of swap, so I'm not going to go into details of that. We've seen that already. Once again, it depends on the system. Sometimes it's easy to do this and not so easy to do a C0 gate, so you can use a swap gate as an equivalent of 2-qubit gates. And then there are some important 3-qubit gates, important in the sense that they have they are usually reversible gates. So one of them is the so-called Toffoli gate, which can be seen as a control NOT gate, so two controls on the signal, where you can see you have a diagonal matrix. So it's 8 by 8 now because you've got 3 qubits, and then the only change is in here, in this part here, where you swap, when you do a swapping of the qubit when you are in a specific state. You have also a swap on the 3 qubit gate, so the equivalent of the 2 qubit swap gate, which is called sometimes a Friedkin gate or a control swap, which is 2 swaps depending on a given control. So the matrix would look like this. So we're not going to go into those very much. We will stick to single qubit gates and 2 qubit gates, but just for you to be aware of the existence of such 3 qubit gates. So then we said, so now we have gates, we can have quantum circuits. We've already seen before, so we can do, we can apply gates in series. So we go from left to right. So that means that we take the first psi state, the qubit state, so we apply Y gate first and then the X gate first. And if you remember, X and Y can be seen are in fact in physically quantum operators, so they are measurements, operations, physical operations done on a physical system. And they are not necessarily reversible, so that means the order is important. So that's why when we go from left to right, so we do Y and then X, that means that if we want to write it in terms of quantum mechanical operators, as we've seen, that means we apply Y to the ket vector psi first, and then we apply the X operation, the X matrix, the X operator onto the result of Y and psi. Okay. We can do gates in parallel. So for that, so if we have 2 qubits and we have 2 gates in each of them, then we can basically put them together by using the tensor product operation that we've seen. And I put back here a tensor product operation between the 2 particular operations, single qubit here, Y and X. So if you remember what we said, the rules, so how to construct that. So you start from the Y and the X 2 by 2 matrix, and then each of these coefficients for the Y matrix will be applied to the X matrix. So you've got now these 4 parts, and then each of them can be applied to all of these. So there will be a 4 by 4, 4 by 4, 4 by 4, and 4 by 4. So here you have all zeros. Here you will have all zeros as well. And here you will have 0, I, 0, and here 0 minus I, 0. And then you went from a twice 2 by 2 matrix to a 4 by 4 matrix. And then you can construct a bigger space with more qubits like so. And in particular, one operator that is important is, as I said, the Hadamard gate, the superpositioning operation. And the reason is because, so we've seen in an example, that if we apply, so the tensor product Hadamard on 2 qubits, and if we start from 2 qubits being in the initial state 0, 0, then when we apply this H2, so H cross H operators, which look like this, to the 0, 0, so this is already a tensor product. So this tensor product of the qubit 1 and qubit 2. Then the vector, the 4-column vector would be 1, 0, 0, 0. So if you remember, let's put that down. So when we have 2 by 2, we have the 4 ket vector, where the correspondence is that the 0, 0 will now be 1, 0, 0, 0, the 0, 1 will be 0, 1, 0, 0. The 1, 0 will be 0, 0, 1, 0. And the 1, 1 for 2 qubits will be 0, 0, 0, 1. Okay? Whereas for this one, we recall that this is already of course, it's not enough space. Where is the So for this one, we have 0, 0, which is already, as it is, a tensor product of qubit 1 and qubit 2. Okay? And then if I apply this Hadamard gate, so this 2-qubit Hadamard gate, which is a 4x4 matrix, onto this specific state, then I end up with a state of superposition state of all the 4 possibilities. So this one, this one, this one, and this one, which looks like this. So 0, 0, plus 0, 1, plus 1, 0, plus 1, 1. Again, which is, if you remember, a typical 2-qubit state that we define, where we define it more generally with various coefficients, A, B, C, D, or alpha, beta, gamma, delta. And here, in this specific case, all the coefficients are the same and weight of 1/2. And we can do that for n qubits. So sometimes we write this H2, Hn, but we can write it like this, with this sort of tensor product notation from 1 to n for n qubit, or also like this, where we do the power of n, but in tensor product type of form. So that would be the Hadamard transform. We call it the Hadamard transform on an n qubit register as opposed to a 2-qubit register like I have here. Right. And then so we saw one practical case, and we're going to see the second one. So the first practical case that we've seen, so I'm not going to go back to that, was how to create one of the 4 Bell states, so in particular the 5+ Bell states, which is one square root of 2, 0, 0 plus 1, 1. So what we demonstrated, so we saw how we can go from the circuit, or rather the calculation, the computation to the circuit. And so what we demonstrated is that at the end, so when we start with 2 qubit in the initial state 0, 0, which is this state, then if we apply first Hadamard gate onto qubit 0, and then a control NOT gate onto between qubit 0 and qubit 1, then we end up with this state. Okay. So first is initialization of the 2 qubits. Second is Hadamard gate on the first qubit, say Q0. Then now this 2 qubit becomes Q0, Q1, 0, 0 is transformed into 1 square root of 2, 0, 0 plus 1, 0. And then, so where you transform the qubit 0 into superposition of 0 and 1. In terms of operators, what we did is, in essence, so we did tensor product in terms of operation between Hadamard gate and identity gate. So for that, we have the Hadamard gate and the identity gate. So this applied to qubit Q0. This applied to qubit Q1. So if I write it like this, so I've got Q0. So what I do here is I apply the Hadamard gate on this one. And what I do here effectively is I apply the identity gate, although I don't write it as such, but that's what I do. And so what I do is I take the tensor product between these two. And so I go from Q0, Q1 to Q0, Q1, okay? And then I apply the operators hi, so I can call this operator k, where k would be the tensor product h and then identity. So we did that. So again, this is on qubit Q0, and this is on qubit Q1. And if I do the tensor product of that, I obtain this 4x4 matrix. So I have 1 square root of 2, and then I've got 0, 0, 1, 0. And then I have 0, 1, 0, 1, and then 1, 0, minus 1, 0, and then 0, 1, 0, minus 1. And now I can apply this to this qubit that is now transformed into this one. Because I did superposition, I applied the Hadamard gate. Sorry, I can apply this to the state 0, 0. If I start with 0. So I can apply this to 0, 0, and then I will obtain at the end the 1 square root of 2, 0, 0, plus 1, 1, plus 1, 0 state. So that's the first stage. So far we are at here. And then the next step will be to do a control NOT gate. So I start from here, from this one. And so in order to do that, so here's the full operation that I just described. And then we do a control NOT gate between Q0 and Q1, and this is the control NOT gate. To now this specific ket vector, 4x4 ket vector, so 1, 0, 1, 0. So the control NOT gate looks like this, and if I multiply it to this state, I obtain 1 square root of 2, but this time I have 1, 0, 0, and 1, where this is for the 0, 0 state, and this is for the 1, 1 state, as we see here. So I end up basically with the Bell state phi plus, which is 1 square root of 2, 0, 0, plus 1, 1. Okay? So again, you can see that this is only half of the computation done on the board, and this would require the full calculation in order to show with a simple circuit that in order to get that state, all I need to do is to write it like this, where I have the Hadamard gate, and then I've got the C0 gate between 0 and 1, and then at the end here, I obtain the Bell state psi plus. Okay, so you can see how the quantum circuit representation is a lot easier to handle than the computation part. Right. So the second case that we started but not finished is the case of the so-called quantum teleportation. So again, the idea is to go from state characterization to the quantum circuit at the end, except that this time is going to be a bit more complex than that. So again, I'll remind you quickly what teleportation is. So teleportation means that you take a given state, in this case some people, and you want to teleport them, you want to put them without actually physically moving them from one place to the other. So quantum mechanics tells you that you can, but you need to fulfill a few but important requirements. So the first one is that as there cannot be any cloning, and the non-cloning theorem in quantum mechanics tells you that you cannot clone a quantum state, so you cannot make a perfect copy. So that's a first principle. So that means that in order to move a state from one place physically to another, that means you need to destroy the system in the first place in order to reconstruct it somewhere else. Okay, they cannot be same system cannot be in two places at the same time. Okay, that's the first thing. And in order to do that, well, you need to retain the information. And as you cannot make copy, the only way you can retain this information is that if you can entangle, you can do some entangling operation between the original system and another system that will become the original system. Okay, so you need to have entangling and entanglement. So you need to entangle. We need to entangle you if you want to teleport you with some particles of you that will conserve. So this entanglement will conserve the memory of you in order to reconstruct you somewhere else. Okay. So at the end of the day, quantum mechanics tells you that it is possible because, well, you and I are made of atoms, molecules, so they're all the same. Whether carbon atoms, whether they are somewhere in one place or the other, they are the same. What is different, though, is the quantum state of a carbon atom in one place will be different than the quantum state of a carbon atom in somewhere else. And that's what quantum teleportation does, that you need to know, you need to be able to entangle, to preserve the quantum system in the first place, to entangle with some others that have nothing to do with you so that they can become you. Okay? And that's why the third step is at the end, precisely in order to make sure that this new system is you. We need to make adjustments so that we are sure that this is new and that we have not teleported, because at the end of the day, you just teleport information. So if you get the wrong information, then you may end up with making the teleportation of something else, of someone else. So how do you do that in practice? So of course, as I was saying, if we do that on people, this is not for tomorrow and not for the day after. This is going to take a long time, if ever possible. But on the other hand, we can do that on qubit, on single qubit, and in fact, it has been done on photons. We managed to teleport the state of photons. But let's have a step back. So what is the system? What do we want to do? So the easiest system is you need 3 qubits. So the first qubit you need is, so say your qubit C is the one you want to teleport. Okay? And then you need a source of entangled qubits, so A and B. And so A and B will be entangled together so that you will do a specific operation between A and C. This is called a Bell state measurement. So that what you do is you destroy the state C, you transfer it in a way to A, and as A is entangled with B, what you do is therefore you transfer now the original state C to B, and now B becomes C. Okay. So for that you need several operations. So the first one is you need to start with your teleporting qubit. So this is psi C. Then you need, as I said, to create a pair of entangled qubits, A and B, that have nothing to do with C to start with. Okay. Then you make a so-called Bell measurement between A, so one of the 2 entangled qubits, and C. You will get a specific result. So that is a measurement, so it's a classical result. So then you transmit that result to the station B. And then B, without measuring, so at the station B, without measuring the other entangled qubit B, will make a write operation, so a write gate, onto the qubit B in order to modify it so that B now becomes C. So at the end, what you did is you started with qubit C, you destroy it somehow, and you transfer the information from A to B, and with B, you made an adjustment so that B now becomes C. And what you effectively did is you teleported C from that place, so that physical place, to this physical place. Okay, so now C has been teleported onto qubit B. Okay, and all of this is spatially separated. That means you have a spatial separation and therefore a teleportation by the sense that I gave before, that you don't take the photon and bring it. So the photon, if we talk about photons, this qubit C here was not taken from here to there, and yet the information was. Okay. Right. So how do we do this? So we want to teleport qubit C. So the state that we want to teleport will look like this, where you have A0 of C plus B of 1C. So this is the most with coefficients A and B. If you remember, coefficients are complex coefficients and so on. But where A and B, so A0 plus B1 is the most general qubit state you can think of. So you do not make any specific assumption on it. So let's see how you really start from the beginning. So really starting from the beginning means what? Means that you have 3 qubits, A, B, C, and then all of them to start with can be in a given known state, say the 0 state. So the first step is that you need your qubit C. So this is, so let's move this. So the qubit C will be in the 0 state. So that's what I wrote there. So psi of C will be 0, C. Okay? So not the state you want to teleport because it's not yet in a superposition state. That's first of all. And the second of all, you need, the first step is that, so you need to take 0. And the second step is you need to have entangled qubits, A and B. So first, psi of C is in the state 0C. Okay? So this initialization. So the reason why I write this is, as we will see today, will lead me to, as I said, the so-called Birefringence criteria for building a quantum computer where initialization is the first step. Then you need an entangled pair. So entangled pair of qubits. So A and B. So say in the state psi minus of AB, so if we recall that state, so it's 1 square root of 2, and it's 0A, 1B minus 1A, 0B. Okay? So now I've got qubit C, qubit A and B. So if I want to put the whole 3 qubit system together, then I have psi of ABC, or rather CAB, where I put 0AB, where I mean that C is in the 0 state. Okay? That is because the next operation will be to put C in a superposition state to be teleported. So that state, so what I wrote is something like this, is the initial state, will be psi 0, then tensor product with psi minus AB. Okay? This we've seen before, can be seen simply as a product state between 0C times 1 square root of 2, 0A, 1B minus 1A, 0B. And that will give me, so 1 square root of 2 of 0C, 0A, 1B minus 0C, 1A, 0B. Okay? So 0C, 0A, 1B minus 0C, 1A, 0B. Right? So far so good. So what we've done here is we have a source of entangled state. We have a qubit C that is in its initial state, and now we have a 3-qubit system altogether. Okay. So the next step will be to apply Hadamard gate to qubit C to be teleported. So Hadamard gate means that we go from the 0C to general state A0C plus B1C. Okay? So I can do that by applying Hadamard gate with coefficients that, known coefficients, any coefficients I want. So that now I go from this state, which I called 0AB, to, so by applying H onto 0C, onto psi CAB. Okay? So what I do is that for each of these 0C, I transform it into A0C plus B1C. Okay? So now this becomes A0C plus B1C. Okay? So that means that now, so this is step 4. So that means that now psi of C A B is basically A0C plus B1C, and then times 1 square root of 2 0A 1B minus 1A 0B. Okay? So I can multiply all of those together, so this by this, plus this by this, and then this, and then this. So I end up with 4 terms. So we'll have the first term, so A0C 0A 1B, and then A0C minus A0C square root of 2 1A 0B. And then same for B. So let's put them together. So if I have first the A's, so I'm going to have A square root of 2, and then 0C. So remember always the notation where a tensor product, I can put qubit 1, 2, 3 into the same state. So 0C and these two will become 0C, 0A, 1B. Okay. Then minus 0C, 1A, 0B. Okay. Plus the second case where it's B1C and then times all of this, so plus B over square root of 2, and then I've got 1C, 0A, 1B, and then minus 1C, 1A, 0B, okay, which is what we have there. So again, and again, what I did here is that what I have here is I've got 0C times this as a reminder, and this I write it as in like this, okay? Right. So now here comes the trick in a way, because step 5 consists in fact in rewriting this state here into this complicated state. So I'm not going to do it completely. I will let you do it, but I will write what it looks like. Okay. So psi CAB, well, we can verify at least that works. So phi of CAB, so is this, and what I'm saying here is I can rewrite it as a 1/2 of 4 terms. And in these 4 terms, I now sort of separate the B side from the A and C side. Again, we talked about this before, but in a way, the way to see it is that A and B are entangled together. And then here I'm going to make a joint measurement between C and A. So in a way, what I'm going to do now is I'm going to entangle, so to speak, or at least jointly associate C and A together. But as A and B are linked together, that means C, A, and B are linked together. So I can rewrite, and you can show that it works. I can rewrite this combination of CAB states into a combination of CA and B states. And I can make appear 4 terms, which are the 4 Bell states now between C and A. So in a way, you can see it's not exactly true, but I transfer the entanglement of A and B to C and A. Okay? So what I'm saying is that I can rewrite this like so. So psi minus CA, one of the 4 Bell states, but between C and A. So we'll write that after. Times minus A 0B minus B 1B. Okay, so here I dissociated 0 and C and AB. Now what I do is I separate CA and B. Okay, plus the other Bell states, so psi plus CA of minus A 0B plus B 1B, and then the 2 others, which are plus phi minus CA times, this time is A1B plus B 0B. And then the last one, there are 4 Bell states, so psi minus and plus, and phi minus and plus. So the 4th one is phi plus CA of, this time, A1 B minus B0 B. Right? Okay. So how do we demonstrate that? Well, let's have a look. So I can recall the 4 Bell states, this time for C and A. So the 4 Bell states for C and A are, let's write it in, I don't know, in orange. So this one would be square root of 2, and then if you recall, so C and A, that would be, so the psi minus would be 0C 1A minus 1C 0A. Okay, so that's for the first one. For the second one, it's the same except that we have a plus here. So it would be 0C 1A plus 1C 0A. Yep. For the phi minus, we have again 1 square root of 2, but then we have, this time is 0C 0A minus 1C 1A. And for the last one, it's the same except that we have a plus. So it's 1 square root of 2. and then 1C, sorry, 0C, 0A, plus 1C, 1A. Right? Right. So how do we show that this indeed will give us that? Well, we can have a look. So for instance, when I will take this state, I'm going to have 1 square root of 2, but I'm going to have 0C, 1A, and then 0B. So 0C, 1A, 0B will be here. Okay, so it appears here. And then I'm going to have, say, 0C, 1A, 1B. So 0C, 1A, 1B is not, no, 0C, 1A is not here, but it's probably somewhere else, and it's probably cancelling. So 0C, 1A, 1B appears here. And in fact, it does cancel, because if you look, I've got 0C, 1A, 1B, I've got 1 square root of 2 minus B. And here I've got 0C, 1A, 1B, and I've got square root of 2 plus B. So these two terms cancel out. Okay? So this one do not cancel out, but this one cancel out with this one, for instance. Okay? And so on and so forth. Okay? And I carry on. And most likely, there is another 0C, 1A, 1B somewhere, so that there's a 2 coming up, so that the 1/2 goes away. And all I have left is A over square root of 2 for 0C, 0C, 1A, and 0B, with the minus, and the minus is here. Okay? And so on and so forth. So I'm not going to do it all, because it's going to take me an awful long time, and with the high chance of making mistakes, and not that interesting, but I highly suggest that you do it yourself. And by developing all of this, you will see that either terms do sum up or terms do cancel out, and so at the end you should recoup that. Okay. So, all right. So now we are at this stage where we have the full psi CAB system between qubits C now to be teleported, and qubits A and B entangled. And what we do now is so now we wrote it in a way in the CA basis, because we've got CA, 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 and CA. And what we do here is we make a joint measurement between A and C. And we look at what it is. Well, if we make a joint measurement between A and C, we should end up with one of these 4 Bell states, right? And if we end up with one of these 4 Bell states, okay, so we make a so-called Bell measurement, so this one, this one, this one, this one. That means that we make a measurement, so we collapse the whole system into one of these 4 possibilities. We have no more a superposition of this, because we made a measurement, so we have either this, or this, or this, or this. But that means that if we have one of these 4, we have to have as well to collapse the B qubit into the complementary qubit that goes with it. So what I'm saying is that if we measure this while doing the joint measurement A and C, that means the B state is also in a given state, which is going to be this one. Okay, so this is B, right? Of course, we may have found something else. We may have found this state. Then in this case, B will be like this. Or this state, and it would be like this. Or this state will be like this. And what we can see is that, so depending on the result that we found here, that's why you can see here there is that this radar where you say, on the other side, you say, hey, I can tell you what I found. So I found this one, this one, this one, or this one. And you need this information, and you need to transmit this information, because you can see that if you found this result, then B is in that state. And that state is precisely the state to be teleported, okay? Because that state, I can rewrite it as A0B plus B1B. And that's in terms of qubits. Qubits are all the same. This is equivalent to qubit C to be teleported. The only difference is that there is a sign here, an average sign here, that doesn't matter in terms of the state of the qubit I have here. And this state is indeed what I wanted to teleport it in the first place, which is A0C plus B1C. And the fact that the index has moved from B to C doesn't matter, because it's qubits. Qubits is a 0 and a 1, so whatever state there is, it has to be 0 or 1, so whether it's index C or B, doesn't matter. Here it does matter in the sense that now what we actually did is that B was somewhere else, was physically somewhere else, so what we did is we transferred information and teleported information from C to B. And that's what's important. So there are 4 measurements possible, 4 outcomes possible when you do this Bell measurement. So this one, this one, this one, or this one. And if we were in this case, you can see that you recoup your teleported state. So you're done. That's it. Good. But you can see that if you found one of the other 3, then you don't exactly have what you would like, because in this case you have minus A0B plus B1B. So it's not that one, okay? In this case, you have A1B plus B0B. So here you invert it. And in this case, you have A1B minus B0B. But it's okay, because what you can do, so usually we talked about, so station A and station B are these 2 people that know each other, so Alice and Bob, say. So Alice on station A, which made the measurements, can tell the result that she found. That's okay, that's allowed. She can tell Bob, look, I found this result. Then in this case, Bob says, okay, cool. Then I know, I have nothing to do, so this is it. This is teleported. But I could have this one, so Alice said, hey, what I found is actually this state. So Bob said, okay, well, it's almost there. The only thing I need to do is that if I could invert 0 and 1, so 1B and 0B, then I end up with this state. So in this case, when the station A transmits the classical result to station B, then in this particular case, what station B needs to do is a single qubit operation, which is an X operation, which is to reverse the qubit. Again, you're not measuring it. You do a qubit operation. Say, okay, fine, I apply X to that. Because if I apply X, then, I permit 0, I swap 0 and 1, and it's okay. I end up with this state, which is what I wanted. And then same for this one and this one, except that it's not going to be the same operation, it's another operation. So in fact, what you can show is that for psi plus CA, you need the rotation along the z-axis, again, the Bloch sphere. For this one is along the x-axis, so it's this A, so it's the knot, the reverse qubit. And then for this one, you need to do a rotation along the y-axis, or you can do, which people do in order to not to multiply many gates, but you can apply x and y, which is the equivalent of applying, x and z, which is the equivalent of applying a y. Okay? And then that's it, done. So you're done. So depending on the 4 results that you measured at station A, that Alice measured at her station with this joint measurement, then she transmits the result, and this is transferred. This result is transferred to Bob, to station B, which can then decide to do a single qubit operation in order to recoup the full teleported state. Okay, so we see the three steps I mentioned. So one, you destroy your original state, and which we did, because here we see as it was here no longer exists because it's been measured by Alice on station A. Then we entangled the information of C with a pair of entangled qubits A and B. So that we did that. So this is this operation of this through this Bell state measurement. And then we make some adjustment to the B qubit now in order to recoup, to make sure that we recoup the C qubit that we wanted to teleport it. And that's this step here. Right. So what does it look like in terms of circuits? Again, knowing that, so this was sort of through calculation. And in terms of circuits, well, it looks a lot simpler. Might need some translation, but it looks a lot simpler. So what do we do? What did we do? Well, we see the state to be teleported, C, okay. Then we have the two qubits A and B that are entangled. So the three of them can start at the 0 state, so 0, 0, 0. Okay. So first, one thing you want to do, you can, so you create a Bell state. So this is this part. We've seen that already. There was practical case 1. And so what you do is you do a Hadamard gate on B, for instance, and then you do a control NOT gate between A and B. This will give you the state, the entangled state AB. Okay. Then here, we are step 4 here. Here, you make you make the state. You make the state, CAB, phi CAB, sorry. So you got now the entanglement between C, A, and B. You do a Hadamard gate on qubit C in order to transform it into a superposition of the one you want to teleport. So at this stage, you have a 3-qubit system, the full-fledged 3-qubit system, which is that one, that you can rewrite into this one. And then what you do here is you do a joint measurement, the Bell measurement between C and A. So remember, this sign is the measurement sign. So you end up with the classical result. So when you have a classical result, you've got 2 bars. And depending on the result that you found, so you make an operation on qubit B or not. It depends. Here you don't do anything. Here you have to make an operation. So it could be a succession of X, Z, or just X, or just Z, or nothing. But you need to, depending on the result here, to adjust eventually this, potentially, this qubit B in order to transform qubit B into qubit C. Okay? So this is the classical adjustment part that you need to do. So it's classical adjustment in the sense that it's classically given by the joint measurement, but again, this qubit, as you can see, has never been measured. Okay, so this qubit remains a qubit, remains a quantum bit of information. Okay. And here, C has been destroyed because it has been measured. A as well, but A was an ancillary protagonist here in a way. Okay. So here we go. So this is an example of a practical case of how you make teleportation. So quantum teleportation, in that respect, is done so it's used a lot in quantum algorithms. So you will see in some examples. So it's good to transfer from one place of your quantum computer to another to transfer information, or to entangle, or to be able to teleport your state from one place to the other. So it's used a lot in some algorithm in order to be used as a box, as a toolbox somewhere in your algorithm. Okay. Right. So this has been done experimentally. So how this was done? This was done with photons. So I'm going to show you here. Well, I'm going to explain the experiment here quickly, and then I will explain how physically we obtain that. So here's the system. So this is an article that was published in 1997. So what they did is they had an issue. So we've seen the same scheme what we just saw. So we have the two protagonists. So we have Alice and Bob. We have a source of entangled photons. So they call it an EPR source for Einstein, Podolsky, Rosen, but whatever. What you need to know is that here A, B are called 2 and 3. So 2 and 3 are entangled. And then you have the initial state 1, so the C state. And what you do is you make here a BSM, so Bell state measurement at Alice's side. Alice has a result, so she transfers through a classical channel this result to Bob, where Bob will take now the second qubit from the entangled pair, adjust it depending on which operation he needs to do in order to get the teleported state. Okay? So how was this done experimentally? So for this, and I'll explain that afterwards, so for this they use optics. So what they've done is they use a particular crystal, so a particular optical crystal, this is this part here. And what they've done is they sent a UV pulse of light, so it's a laser pulse. And by doing so, by nonlinear optical effects, what they created here, you can see here two lines going off, and these are actually photons, a pair of entangled photons that came out of this nonlinear crystal. So they managed to that way to create a pair of entangled photons that's done in polarization, and I'll explain to you in a minute how that works. So these are the photons 2 and 3. So in this case, in our scenario before, is A and B, what I call A and B. And then what they've done, so, there's the theory and there's the practice. What they've done in practice is that they didn't make, they make use of this creation of twin photons, of entangled photons, by having a mirror here and sending back the laser into the nonlinear crystal so that they could create a second pair of photons, which they call 1 and 4. Okay, so 4 does not appear here, and the reason why is because 4 was only used here as a detection channel so that it can allow for the arrival of 1 onto their Bell state measurement here. Okay, so it's a trick that we do is that you create a pair of photons, and then what you do is you use one of the pair, because they're twin photons, so they've created at the same time. So you use one of the pair to, what we say, to herald the arrival of the other one, or to announce the arrival of the other one. So this is a sacrificial photon. So 4 is a sacrificial photon in order to say, okay, now I've got 1 in my circuit. Okay, and what they've done here, they use a polarizer, and we've seen before that using polarization optics, you can actually make Hadamard gates. That's what they've done. So now they have this initial state, which is in a superposition state. So so that would be the equivalent of the C qubit that we've seen earlier. And then they take that qubit, they take one of the photons of the other pair that they created here, so photon number 2, and then they make here, on this site, a joint Bell measurement, which is simply actually to use a so-called 50-50 beam splitter, where you mix the two photons together and you look at the result you get here. The result you get here are polarization results, so you look at the polarization state of the two photons. And depending on what you find, so polarization state will be either given by this one, this one, this one, or this one. Or if you remember, we said we can encode the polarization state, so say horizontal polarization or vertical polarization on 2, 0, and 1. Okay? So by measuring polarization state here, they can tell which qubit state are 1 and 2. Therefore, they can know which Bell state they measured for Alice. And then once they have the result, then they say, okay, if in this case do nothing, in this case make a Z transformation, X transformation, or a Y transformation. So they send that to Bob's side. So Bob's side is the other photon of the pair that goes into a particular state where you can change the state, you can rotate the state, and look at the. So this is the analysis part. At the end, you make a measurement and make sure that what you had was indeed what you teleported. Okay. So it's the same scheme. So it's the exact equivalent of that with photons and polarization state of light rather than qubits 0 and 1. You encode the qubits 0 and 1 onto the states onto polarization states. So 2 and 3 here would be the equivalent state that you have here, A and B, except that in this case they are called 2 and 3. Okay. So they've shown that. So this was done. So that was in 1997. But then, since then, as I said, it has been used, and it is used for many practical application and algorithm to be used. So this was done with photons, and people have done that since with spins, electron spins, or also atomic levels of energy from single atoms or single ions, and so on and so forth. So there are various ways of doing teleportation. It's not an easy operation because you need 3 qubits, you need an entangled pair of qubits, and you need your initial state to teleport. But it can be done, and it has been done in many systems. Right. So to finish this part, so now I just want to go back to how, so a bit of physics here, how we create entanglement with photons. I mean, of course, this is the idea is not to make a full nonlinear optics course. That's not the idea at all. But just to give you enough insight so that you understand where it comes from. So first of all, let's go to nonlinear optics, or I'd say nonlinear physics in general. And for that, let me give you an intuition of what happens when you send light onto a piece of crystal made of atoms. So when you send light, when you send light onto a crystal, okay, so made of many atoms. Atoms are made of a nucleus, which is a positive particle, and electrons, which are negative particles. And if you send light onto it, you send an electric field that will interact with the crystal, and in particular will interact with the electrons, with the charge. Okay, it's going to potentially move the charges. Okay, and the way you can model each of these atoms is by saying that you have indeed, as is written here, you have a positive particle linked to a negative particle, the electron. Okay, and this is the nucleus. Okay, and linked by a spring. Okay, with a certain constant K, for instance. Okay, so this would be a spring. So when you send light onto it, what you do is you basically make the electron moves, because the electron will interact with the electric field, and therefore the electron will move. Then the light passes away, and then the spring makes sure that eventually the electrons will stop moving, interaction will stop, and then the crystal will come back to its initial state. Okay. So how can we simply model that? So we can simply model it by a so-called elastic model. So we say that we apply Newton's law. So Newton's law, okay, Newton's law tells you that the mass of the electron times acceleration is equal to the sum of the forces applied. And here we have three forces. So the first one is the incoming force of the electric force, so FEL. Okay, this is the force. So there's the external force that might not be present or not, that might or might not be present. So this would be the charge of electron Q times the electric field. This is electric force. Okay. The second force will be the spring constant, so the spring force, okay, the restoring force. So this would be something like minus kx, where if I assume that I am along the x direction, okay, where k is a spring constant, right? So that would be spring. And then I have to add another force, which is what we call usually a viscous force, which is basically that, ideally when a spring, when there is no restoring back to the original state, then this oscillation can carry on forever. And of course, this is not possible. Eventually, there is what we call dissipation, and eventually this spring is going to stop. And for that, I can model that by a friction force that is going to be something like minus gamma v, where v is the speed of the electron. Okay. This is standard classical mechanics. Nothing very fancy about it. Just standard classical mechanics. So, and for v, in this case, would be, so this is the viscous constant, gamma. I can call it gamma. And v would be dx over dt, again, along x in this particular case. Okay? So if I do this, so as everything is going to be along the x-axis, I'm going to remove the vectors. The acceleration is the second derivative in time. So that would be this part. So actually, sorry, I'm going to call this one m gamma so that I can remove the m afterwards. So if I write this, I've got m x, so second derivative of x in time, equals the electrical force, so that's going to be Q is minus E, okay? And I've got the spring force, so that's going to be minus Kx, and I'm going to have minus m gamma dx over dt for the viscous force. If I divide by m on each side, and then I put everything in one side, I end up with d squared x over d2 plus kx plus over m plus gamma dx over dt. Sorry, I'm going to write it in different order. So plus gamma dx over dt plus k over mx, so that's written here, equals minus E over m, and then the applied electric field that put all of this in motion. Okay. So I can stop here, but you can see in this equation here that there is another term here. And also, so this is usually called omega 0 squared, which is the typical oscillation frequency of the spring. Okay, so this will have a typical oscillation frequency omega 0. So this looks exactly like what's on the board, except that there is something else here on that board, is that there is that part here. And this part here is it's what we call an anharmonic potential. Okay? Anharmonic potential. And so here, this is classical mechanics, but, and I have a spring, so I have an oscillators, I have something that oscillates. But an oscillator, so it can be a mechanical oscillator, it can be an acoustic oscillator, it can be any kind of oscillators. When it oscillates in this regime here of minus kx, it's in the linear regime. So that means that you have a linear dependence with the movement. But this is an approximation in a way, because any oscillator can also have higher order terms. Okay, they can have what we call anharmonic terms. So the most general case is ax2, but you can also have bx cubed plus cx fourth, and so on and so forth. So you have higher terms. Okay, why is this? Because this is basically a Taylor expansion of the harmonic oscillation. And this is true for a spring in physics, but this is true for many things in life where you have a harmonic oscillation. You can approximate it to a linear system, but you can also have more complex oscillations, and then you have to incorporate these terms, which are anharmonic terms. Okay? And that's true for sound waves, for instance. It's the same thing for sound waves. Okay? So what it means here, it means that when you have your crystal full of atoms, each atoms, we model this by this simple harmonic oscillator where you have many atoms linked together, and then you have on each of them you have electrons attached to it. That means that, and in fact I'm telling you, depending on the strength of the electric field, you can remain in the linear regime. But if the electric field that comes in, so the very thing that moves the electron is strong enough, then you can start to hit higher orders, and you can start to have anharmonic terms of x squared, x third, x fourth, and so on. Okay. So again, it's like having a harmonic oscillator. Then if you start to have this mechanical oscillator, you can be in a regime where this does not hold anymore. You need to have higher terms. So optically, what it means here is that, or for the electron, rather, what it means now is that you have these higher terms. So let's stick to the first order. Okay, so this term. And now let's have a look at the solution of this problem. So if I did not have this term, this equation is known. We can solve this equation, and for that, for a simple case, and the simple case is when we assume that the electromagnetic wave is a plane wave. We talked about this before. And the easiest way to see light is to see it as a plane wave for the electric field. So I can say for a given frequency, so E is going to be E0 cosine of omega t, where omega is the frequency of light. Okay, so therefore the wavelength, therefore color, red, blue, red laser, blue laser. I talked about UV laser earlier. Okay. So I send that in, and typically, if I want to solve this problem without that, then what I'm going to do is to look for solution of the form x of t. It's going to be something like capital X, I mean amplitude, and then cosine omega t. It's going to look like this. Okay? In fact, I can write it. Okay, is this solution to that? The answer is yes. So I can do that. I'm not going to do that here because it's not the point, but this is what we do in physics. We say, okay, fine, I look for a solution, and what I find is that what we call I find a dispersion equation that basically provide the behavior of this crystal under electromagnetic excitation. But now what I want to get to is that because I've got higher terms, now I've got a square here, right? So that means that the solution I'm going to look for will be all, again, the same as this, because I come with this. So what I'm saying here is that if I come with a certain oscillation in time, I will excite my crystal, I will sort of print this to my system in the same way, which seems fair enough. But now if I have these higher terms, that means I have an x squared here. Okay? So x squared means that I have x0 squared, and I have cos squared of omega t. But cos squared of omega t, as you can see here from trigonometry, can be decomposed as 1/2 plus 1/2 cos 2 omega t. So in other words, what it means is that now I've got a nonlinear response of the crystal with the light coming in. So in other words, that means that I came with a frequency omega, the light interacted with this frequency with my crystal, with all my systems, and if I'm in a nonlinear regime, so if it's strong enough, the condition is that you need strong enough light to start to hit these terms, which are usually very low. Then you have an harmonic potential, and then you have this term of x squared. And then x squared gives you now frequencies of 2 omega. So what does that mean now is that if I came up with a given color, so omega, say, red, then now I have red again, but I also have blue light of twice the frequency. Because that's what it says, 2 omega. So it's twice the frequency, so twice the energy. And you remember, in terms of wavelengths, it's the other way. So red light is less energetic than blue light. So that means that now I've got red light coming in, there's red light coming out, and blue light with higher frequency coming out. This is what we call, so it's a generation of higher harmonics. Okay, so because we said higher harmonics because we have twice the harmonics that we started with. And this is what we call second harmonic generation. Okay, second harmonic generation. Again, this is done through optics, but second harmonic generations can be done with other systems, like, again, sound waves, for instance, as long as you are in this regime where this harmonic potential kicks in. Okay. So why am I saying all of this? The reason is because it means now that I can generate different frequencies. And in this case, it's second harmonic in the sense that I've come with omega and I come out with 2 omega. But nature tells you that I can do the reverse. I can come with 2 omega and end up with twice or 2 times omega. That's the exact reverse process of that. It's still a nonlinear process, except that it's a reverse process. And that's how we produce polarization and entangled photons. So now, in the last few minutes, let me try to explain that to you. So we have the same thing here, except that now we do the other way. Okay, so what we come with is And the other major difference is that all of these models are used. It's a classical model. It's a very simple model, but it's good enough to give you intuition of what's going on. But the reverse process is a purely quantum model. I cannot do the same thing, and I'm not going to explain to you how we do this, because you need quantum mechanics, and in particular you need what's called quantum optics. But just to let you know that this is sort of more complex version of that, but it can be seen, and it is, the exact reverse process. Okay? And as we will see, this exact reverse process is interesting because this is going to provide us directly with the entangled pair of photons. Okay? So, and I'll show you, so not today, but I'll show you at some point a demonstration, a live demonstration on how to do that, how we do that in a lab. So, reverse process means what? So I still have a crystal, and I still have a laser, right? Like before. Except that now it's a reverse. That means now, before I had low energy, gave me higher energy. Omega gave me 2 omega. Now I want the reverse process. This reverse process is called spontaneous parametric down conversion. So spontaneous because it's just given by nature. We don't do anything particular. We just, hope. Parametric because you've got 1 and 2, so you've got 3 entities. We will see what are they. And down conversion because now you go from 2 omega to omega. So you down convert light from high energy to low energy this time. Okay. So you're going to tell me, well, but how is this possible? Because in physics, there are 2 laws that have to be conserved all the time. And the first law is the energy conservation. I cannot create energy. And that's fine. I am not going to create energy. I'm going to redistribute energy. So how do we do this? So I take a crystal, so same crystal, and now I send a UV, so we say UV pump, by analogy to classical mechanics, but a UV laser, so strong light with high energy, 2 omega. And what's going to happen here is that by this nonlinear process, one high energy photon has now a probability to split into 2 photons, twin photons, but with low energy. Okay? So now you send h bar or 2 h bar omega, and then what you end up with is 2 photons, but each of them with energy h bar omega and low energy. So typically, again, in terms of light, you come with a blue photon and you end up with 2 red photons. Okay, so one spin. So no problem for energy because 2 h bar omega gives me h bar omega plus h bar omega. So I have, so if my 2 photons, 1 and 2, there is energy conservation with the what we call the pump. So with the let's call it pump here, photon that comes in. Okay. Again, this is a purely quantum behavior that I won't have time to discuss, but just for you to let you know. And now the second ingredient you need is that in nonlinear optics, these crystals can have various properties. One of them is called birefringence. Whatever, let's forget that. So let's write it, but let's forget that. Birefringence. But what we should not forget, on the other hand, is that what it means is that the 2 photons that are going to come out now, if we choose the right crystal in the right configuration, so it's a geometrical configuration. Configuration means axis of orientation, etc., whatever. But if we are in the right conditions, the 2 photons that come out will have orthogonal polarization. So one of them is going to be, say, horizontal state, So like this, I will represent it like this. Remember, oscillation like this. And the other one is going to be like this. Okay? This is what we call a type 2 nonlinear crystal with orthogonal polarization for the twin photons. So up to now, I do not have entangled photons. What I have so far is twin photons. Okay, so I have two photons that come out, one with a given polarization state and another one with the other polarization state. Okay, this is given by standard anisotropic optics. Okay, just trust me on that. And the second thing is when these two photons come out. So first of all, they are separated physically, and also you can show that due to a second conservation, which is the momentum conservation. Sorry, not the moment, the momentum conservation. The momentum conservation tells you that the k vectors, so the momentum vectors, the k vectors, the directions have to be conserved. So the k pump in the middle has to equal the two of them. But because there's a certain sort of leverage between the two, then the two photons actually comes out as cones of light. Okay, so those are the cones of light. So that means that if I look at the upper photon, so upper polarization state, I find, say, vertical polarization. It's called extraordinary or ordinary because it's the various angles of the Birefringence crystal. Forget that. What you need to remember is that the top one will be a, say, vertical polarization, and the bottom one will be horizontal polarization. And now, so you have these two cones coming out. And now the idea is that you tilt the crystal slightly so that the two cones will start to meet each other, and in particular to cross each other into two different points, here and there. You have, if I take two cones, if I make a cut like this, so this is the representation of the two cuts, I have two circles, right? And I have two intersections between these two circles. I have two intersections of the two cones. And the idea here, so we'll go back to that, but the idea is that you actually pick up these two intersections. Because at these two intersections, you have instantly an entangled state that's going to look like this, where all you can tell is that one photon is H and the other one is V, because this is done by construction. But because they are intersecting here, or here is a true image, true color image, you don't know which one's which. So that means that you have to have a superposition state between, if this one is H, then this one is V, but if this one is V, then this one has to be H. And as you don't know, you have to have a plus or minus sign. It depends on the phase, depends on the orientation of the crystal, but you have plus or minus phase between the two. And so what you end up with is a kind of state like this, where you have H1, V2 for photon 1, photon 2, plus some phase V1, H2. And that is precisely the definition of an entangled state where H and V can be 0 or 1. So you have here 0, 1 plus exponential I phi 1, 0. Okay? So this is how you can create an entangled state with photons. So I was a bit quick on that because time is running out, so I'll come back to that. And just to let you know, so next week, hopefully, it will be on Introduction to Quantum Cryptography. And then after that, we will resume on to quantum algorithms. So here is what we are going to cover. If not, then we'll carry on next week on to quantum algorithm and have the quantum cryptography introduction at a later time. So with that, I'll stop here, and I thank you for your attention.